So there are two different types of numbers, and one of those is exact numbers. So exact numbers are going to be counting numbers, like when we count two coins, that two is going to be an exact value. For like eight eggs, those are going to be counting numbers. So in addition to that, there are some numbers from definition. As an example, when it says 1 kilogram is equal to 1,000 grams, these two numbers are going to be exact values because it's from a definition. The value of a kilo is 1,000, so it's the exact value. So the next one is called inexact or measured value. So those are the values that we are going to record from an instrument or by reading a scale. So we are going to record a value, and those are called measured values or inexact values. So you should be able to differentiate the exact values and inexact values. So numbers depends on how they were determined. So scientific instruments have some errors or limitations. And also when we read numbers, we made some human errors. So we are trying to avoid those human errors and report our numbers accurately. So we are going to learn how to read numbers from a scale or from an instrument. So instruments normally give you the value, but when you use a scale, like when you read a temperature using thermometer, we may have some errors. So we're trying to avoid those errors. So as you can see in this example, there's thermometer and you can see the temperature. So by looking at this scale, it's given for every 5 Celsius. So that's the minimum distance between two lines. So if our temperature is going to be like this, now we have to report our data. So it is not going to be 25 Celsius because it's a little higher than 25, and it is not 30 Celsius because it's below 30 Celsius. So it's somewhere in between 25 and 30. So we can record this as 27. Okay, so this is something that we are going to estimate. Okay. So it's estimation based on the scale, and it's a reliable number, and it is not exact. So this can be like 27.2 or 26.8. So if we have a different thermometer, this temperature might slightly deviate from this value. So but based on this scale, we can record our data up to 1's place accuracy. So that's the accuracy we can have on our data. But if you're going to use a different thermometer, like this, so let's say we have a different thermometer, and if that scale has 1 Celsius, yeah, like let's say 25, 26, 27, 28, 29. So let's say our temperature is going to be like in the middle of 27 and 26. So what is the value we are going to record as the temperature shows from the second temperature thermometer?
Would you do 26.5?
Yes, so we are going to record it as 26.5 because it is not going to be on the 26th line or 27th line, so it's in between both lines. So we can record it as 26.5. Now you can see these are two different thermometers. So this is more accurate because gap is 1 Celsius. In this case, it's 5 Celsius. So that accuracy represented by our reading. So this has 1's place accuracy, and this has up to 10's place accuracy. Okay, so let me give you another practice one. So let's say we are going to use the same thermometer, 25, 26, 27, 28. So this time temperature is going to be like this. So what is the value we are going to record as the temperature? What is the value? 27? Yeah, I hear one answer as 27. Is there any different answers?
You probably do like 6.8 or something like that.
Okay. So it is close to the 27 line. It's almost on the 27th line. Okay, so you can assume it's exactly on the 27th line. Okay. Are you going to change that answer? Yes or no?
Yeah, that's a good estimate.
Okay, so if I'm going to record the temperature using this thermometer, I'm going to keep the same accuracy. So since it is on the same, I mean, it's on the 27th line, I'm going to add a 0. So this number tells us it's more accurate compared to this value. So these are two different temperature scales. So then you should have two different ways to report it. So this number is more accurate than this. So that 0 is for the accuracy. So that's something you can estimate. So it's a reliable number. The last digit measured is considered reliable but not exact. So all measured numbers have some degree of inaccuracy, even that not be 27.0, but we can record it as 27.0. So let's try to practice that. So what is the length of this piece of wood? So what is the length of the first one? 4.5 centimeters. Yes, it's a good estimation. So it is not on the fourth line or fifth line, so it's in the kind of a middle. It's 4.5. So when you use the second ruler, so this piece of wood is in between this line, this one. So it's in the middle. So what is the value we are going to record? 4.55 is the correct answer. Now you can see your reading. There's the difference of those two rulers. So you can estimate the 100th place value. Okay, so last one. What is the value?
3.0.
3.0. Okay, so these two rulers are same. And it's going to be 3.0. And from nothing school or from your workplace, they might tell you to drop the 0 because if you miss this decimal point, you might read it as 30. So instead of 3, you might inject 30 milliliters. That's why they're asking you to drop the last 0. But if you're following the scientific rule and the accuracy of your data, you're going to report it as 3.0. Okay, good job. Okay, so next two words are again important, and you're going to see one question from this slide in the exam. So either precision or accuracy, you should be able to understand the meaning of those two words. So precision is how closely your measured values are going to agree each other. Like if you're doing the same experiment 3 times, so let's say you're going to take the mass of an object, and your masses are going to be like 4.24. 4.26 and 4.27 grams mass of a small object. Now you can see these numbers are close to each other. So these numbers has a good precision. So it's agree each other and it has a higher precision. And let's say the actual mass of that object is 4.25. So this is the true value. So if the true value is close to our measured values, then it has a good accuracy. So our measured values or calculated values are close to the true value. So it has a good accuracy and good precision because accuracy is based on the number of trials. So it's agree each other. And also it's close to the true value. But let's say your balance is going to read 1 gram extra or 1 gram extra than the actual weight. And if the actual weight is 3.26 or something like that. So now you can see the calculated values has a deviation from the true value. So in that case, you have only the good, higher precision, but it doesn't have the accuracy because there's an error on the instrument. So yeah, true value is 3.26. Our calculated data deviate from that value. So you can visualize the same thing from these 3 dartboards. So when the dartboards at the center of the dartboard, that's our target. So that's bullseye. So we have all 3 on the target. So it has a good accuracy and good precision. So if your darts are like this, so you can take the same place, but it's deviate from your target. So you have a poor accuracy and good precision. And if your data or darts are all over the board, no accuracy or no precision. Okay, so you can see the definition of the 2 words. Precision is a measure of how closely individual measurements agree with one another. So it can deviate from the true value. The accuracy refers to how closely individual measurements agree with the correct or true value. Experimentally, we often take several measurements and determine a standard deviation. And we covered this topic, so this is in chapter 1. So we covered the scientific notation in last class. So I'm going to skip this slide. So now we are going to talk about significant figures. Okay. So you're supposed to learn this from your math class, but I don't know how many of you have learned this. So I'm going to explain all the rules to count significant figures in all the measured numbers. So keep this in mind. You're going to count significant figures or digits in measured numbers. Only in measured values. You do not count those in exact values. Exact values, no significant figures. No significant. As an example, when you see an equation is equal to 1000 grams, these digits doesn't have any significant digit. So you're not going to count because those are definition or exact values. So when rounding calculated numbers, we pay attention to significant figures so we do not overstate the accuracy of our answers. So then we are going to follow two rules during the calculation and apply the significant rule. So these are the rules that I'm going to explain. So I'll explain this with some examples. So this is the first rule. All non-zero digits are significant. Okay, so as an example, 12.642 grams. So it's mass of object. So there's no zero in this number. All these digits are significant. So we have 1, 2, 3, 4, 5. 5 significant figures or significant digits. That's easiest rule. Second one, 0 in between 0 digits. Significant. So as an example, there are 3 zeros in between non-zero digits. Those zeros are significant zeros. So in this number, there are 1, 2, 3, 4, 5, 6, 7, 8 digits, and all digits are significant. 8 significant figures or significant digits. Third one. Those after a number. Significant with the decimal. When there's a decimal point in a number and have zeros at the end of the number, those zeros are going to be significant. That's an example. 12.65640000. These zeros comes with a decimal point, and those zeros are after the number, and those are significant zeros. So in this number, there are 7 significant digits. So when you write like 450, is this zero a significant zero?
No.
No, because we don't have the decimal point. So if you write 450 like this, so this has only 2 significant digits. So this zero is an insignificant zero. But if you write 450 like this with the decimal point, now that zero is significant. So it has 3 significant digits. Please understand that difference. With the decimal point, this zero becomes significant. So without that decimal point, it doesn't matter how many digits you have. So you can have a number like 6200000. So none of these zeros are going to be significant. Because there's no decimal point. So the first two digits are significant. This has two significant digits. Last zero is to identify non-significant zeros. Zeros at the beginning of a number never significant. How many significant digits in this number? How many significant? Five. Yes, it has five. So zeros at the beginning of a number never significant. So those three zeros are non-significant zeros. So zeros after a number significant with the decimal point. So those two zeros are significant. So there are three non-zero digits. Let's take plus two. Five significant digits. Any question? Last rule. Digits in the coefficient of scientific notation is significant. All the digits in the coefficient of scientific number is significant. So as an example, 1.4094000 and 10 to the power -3. So now it's written in scientific notation. And this is the coefficient. All those digits are significant, whether it's zero or non-zero or zeros after a number. So normally we don't have a zero to begin scientific notation. So all these numbers are significant. So it's 3, 6, 6 significant. Okay, so those 4 rules, 4 or 5 rules cover all the required rules to identify significant digits. All non-zero digits are significant, zeros between non-zero digits are significant. Zeros at the beginning of a number are never significant, and zeros at the end of a number are significant if it contains a decimal point and coefficients or digits in the coefficient of a scientific number is significant. So these are scientific notation. First one has 3 significant digits. Next one has 4 significant figures, and next one has 5. So this table has some examples and also one mistake or typo. So there should be a decimal after 50. So after that zero, there should be a decimal point. So first rule is not a zero. So first one has 2 digits, 2 significant digits. Next one has 5 digits, 5 significant digits. The zero between non-zero digits are significant. So there's a zero in between 2 non-zero digits. So that zero is a significant zero. So it has 3. So next one has 2 zeros in the middle of 2 non-zero digits. So altogether there are 4 significant digits. The zero at the end of a decimal number is significant. So that zero is a significant zero with the decimal point. So this has 2 significant digits. 16.00. So those 2 zeros become significant with the decimal point. So it's 4. The next 2 examples written in scientific notation. So first one has 2, next one has 3. And last 2 examples or 2 rules to identify not significant zeros. At the beginning of a decimal number, or at the beginning of a number, or zeros at the beginning of a number, never significant. And also these zeros are not significant because it doesn't have the decimal point. So those zeros are just a placeholder. So those are not significant zeros. Okay, so we're going to talk about the significant figures in calculation and the rules. So I'll come to this in a minute. So, okay, so let me explain this here. So this is the first rule during the addition and subtraction. Addition or subtraction. Rule is the first number of decimal places. If you're going to add or subtract measured numbers, we're going to count the number of decimal places and we keep the final answer into the biggest number of decimal places. So as an example, let's say 12.6219 plus 14.6. Number 7.1 and 3. We're going to add these numbers. So you can do the addition on your calculator. 913 5 30.5319. Okay, so that's your calculator display. So this is not going to be the final answer. So this is calculator display. Now we are going to count the number of decimal places. This has 4. This has 2. This has 1. The previous number of decimal places in the addition is 2. So we are going to keep the answer into, one decimal place. So we are going to keep the answer into one decimal place or 10th place. So this is the previous decimal place. That's 10th place. Now we are going to round off this number into 10th place. So what is the final answer? 30.5. Okay, so it seems like everyone knows the rounding rule. When you round a number, you're going to count the required numbers. So we need 3, 1, 2, 3. So we are going to drop 3, 1, and 9. So then we look for the first number to drop. The first number to drop is 4 or below. We are going to drop all the numbers after that, including that number, and leave the first number or first written number as it is. So if the first number to drop is 5 or above 5, we are going to add 1 to the first written number and drop those numbers. So that's an example. 12.976. But we're going to round this number into 3 significant digits. So we are going to count numbers from left to right, 1, 2, 3. So those are the required digits. So first number to drop 5 or above. We are going to add 1 to the first written number and write the answer. So what is the answer? 13.0. So 13.0 is the answer into 3 significant digits. So that's rounding off rule. So this is true for addition and subtraction. Fewest number of decimal places. So if you don't have a decimal place, and if your lowest number is in the ones place, we are going to write the answer into ones place. Like this example. 6.21. Well, 3.56. 1. So we are going to add 1, 7, 7. 21.771 is the calculator display. So no decimals and accuracy is up to ones place. So we are going to round this number into ones place. So it's going to be 22. Did everyone understand this? Okay, so next one is the multiplication and division. So during the multiplication and division, rule is fewest number of significant digits. Fewest number of significant digits. Significant digits. in your calculation. So we are going to count on the significant figures for the measured values, and based on the significant figures in our calculation, we are going to keep it for the lowest number of significant figures. So as an example, let's say we want to calculate the area of rectangle, and let's say with is 6.29, and this is going to be, let's say length is like 150. I didn't draw it to the proper scale, but you get the idea. So length is 152.64 centimeters, and width is 6.29 centimeters. How do we calculate the area of a rectangle? Length times width. Now we are going to use these two values. These are measured values, length and width. It's going to be 152.64 times 6.29 centimeters. Calculator value is 6.29 times 152.64. The calculator value is 960.1056 centimeters. That's not your final answer in this class. So you might have this as a choice, but you're not going to keep your calculator as its final answer. This is the calculator display. Now we're going to count the significant digits or significant figures in all the measured values. So this is a measured value, so length. So how many significant digits? 5. It has 5. Good. So this has 5 significant figures. And this is also a measured value. So what is the number of significant digits? 3. So rule is to keep your final answer into fewest number of significant digits during the multiplication and division. Now we are going to round this number into 3 significant digits. So what is the answer? 969, yes. With the decimal. Okay. So now it has 3 significant digits. So if you write 960 without the decimal, it has only 2 significant digits. The other option is you can write this as a scientific notation. So all the digits in the coefficient are significant. Both answers are correct. And because of this reason, some answers may be in scientific notation and your calculator might give you in this standard form. Okay. So it might be in scientific notation. Any question? Am I too fast? Is everyone getting these concepts? Good. Okay, so you can see those rules here, and I have more slides with examples. The least certain measurement limits the number of significant figures in the answer. When addition or subtraction is performed, answers are rounded to the least significant decimal place. So when multiplication or division is performed, answers are rounded to the same number of digits as the measurement with the fewest number of significant figures. So now the numbers of appropriate digits but round off all at the end. Okay. So you can have all the numbers and do the calculation and round off your final answer to the appropriate number of significant digits. So this is the rounding off rule. If the first digit to be dropped is 4 or less, then and all the following digits are dropped from the number. And if the first digit to be dropped is 5 or greater, then the last retained digit of the number increased by 1. Okay, so these are some examples of rounding numbers. And let's practice this with few examples. So let's see how good you are counting on significant figures and rounding numbers. First example, so you're going to count the number of significant figures and then round to these number of significant figures. So I keep 3 significant digits and take it 2 significant digits. Okay, so first number is Okay, so this is how we are going to answer this question. So this is a given number. So you're going to count the number of significant figures for the given number. And then round this number into three significant digits and two significant digits. There are five examples. There are few difficult questions. Does anyone need more time? Good. Okay, let's go over the answers. So let's count the significant digits for all these numbers first, and then we can round these numbers to the appropriate number of significant digits. So how many significant digits in the first number? Five. Good. So these two zeros are non-significant zeros. So we have five. It's five significant digits. Okay. The next one, how many? Four. Four. So first two zeros are non-significant. Zeros at the beginning of a number never significant. So last four digits are significant. But that's four significant digits. The next one, 34,000. How many? Two. Zeros after a number never significant without the decimal. So we need to have the decimal to have a significant digit. The next one, how many? All the digits are significant. So 3, 6, 6, 6 significant digits. The next one, how many? The coefficient has 5 digits. All digits are significant. So it's 5 significant. So now we are going to round that number into 3 significant digits. So when you round this number into 3 significant digits, what is the answer?
The top number,
Yes, first one.
731.0.
So you write it like 731.0 like this.
Yes.
7.31 times 7.31 times 10 to the power 6. 36. Good job. So this is correct. So it's 10 to the power 6. Okay, so this is a big number, and we can't round that number to 731. So it's not going to be the correct answer. So why? You missed a small portion of one of those rules. So when you round a number greater than 1, or if you drop numbers before the decimal point, so you're going to drop these numbers. So this is the cutoff point. So we need first 3 digits. It's 731. So when you drop any numbers before the decimal point, you have to replace it by 0. So you have to replace those 4 digits by zeros. So that's the correct way to round it to 3 significant. So if not, you can convert this number into scientific notation. So that's going to be 7.310600 times 10 to the power 6. Then you can round your number into 3. You're going to drop these digits. So it's going to be 7.31 times 10 to the power 6. So that's the proper way to round a number like that. So into 2 significant figures, we are going to follow the same rule. So we have to drop everything after 1, including 1. So we need only 7.3. So we are not going to write it as 7.3. So it's going to be 5 zeros at the end, because we are going to drop 5 digits before the decimal point. So we are going to drop all those numbers and we replace those by zeros. So in scientific notation, you can write it like 7.3 times 10 to the power 6. That will also be correct. Yeah, both answers are correct, because there's no decimal point for this number. Only first 2 digits are significant. So zeros after a number are significant without the decimal point. Did everyone understand this? Okay. The next one is easy, probably. Yeah, very simple. I'm going to try to move this. I'll try to write the answer again. So next one is, it has 4 significant digits. So we are going to round into 3 significant digits. So simply we can drop the last 0. So once we drop the last 0, it has 3 significant digits. Going to be 0.019. Okay, so round that number into 2 significant digits. We're going to drop 6 and 0. So now we are going to apply the rule. First digit to drop is 6. So we are going to add 1 to the first digit number. So what is the answer? 0.020. So when we add 1 to this, it becomes 10. So 1 goes to this one and it gets to and 9 becomes 0. So we need to have this 0 to have two significant digits. So this number given, it has two significant digits. So now we are going to increase the number of significant digits. So how do we increase the number of significant digits on this? What's that?
Give it a decimal point. 3.4.
What it means? So give a decimal point like this,
3.4 is
like this. Where's the decimal point like this? What do you mean by the decimal point? How do you write that into three significant digits? Yes, I know you know the answer.
Would it be 3.40 times?
Yeah. So the only way that you can write this with the appropriate number of significant digits is using the scientific notation. So you can't write that in standard form with the three significant digits. Because three significant digit is going to be 340. So we can't put 0 here. So we are going to around 34,000 into 340. So it's a big difference. So that's not how rounding works. So we can't put the decimal point like that. So you can convert this into scientific notation and write with the appropriate number of significant digits. I think it's 4. It's 3.40. Again, when it is too significant, because you can keep it like this, or you can write it in scientific notation. So this already has two significant digits. Or you can write it like 3.4 times power 4. This one and this one is same. Both has two significant digits. The next two should be straightforward. So what is the number when you round this into three significant digits? 1, 2, 3. So we counted 3 digits. So we are going to drop all the values after decimal. So first number to drop is 0. So you can drop everything. It's going to be 150. Sorry, 150. So what is the answer when you round this number into two significant digits? What is the answer? 60. So 1, 2. The first number to drop is 5. So we are going to add 1 to the first retained number. So it's going to be 1, 2. So we are dropping a number before the decimal and replace that with 0. So 120 without decimal has two significant digits. Or you can write this in scientific notation. Times the power. Both answers are correct. Next one, it's already in scientific notation, so that's easy. So when the number is in scientific notation, it's easy to round. Okay. So into 3. 1, 2, 3. First number to drop is 6. So we're going to add 1 to the first retained number. 2.71 times 10 to the power -3. Next one is two significant digits. The first number to drop is 0. So we simply drop all the decimals. Now this is going to be 2.7 times 10 to the power -3. Okay, so I think those 5 examples cover the number of significant digits and rounding off to. You need more examples or is this enough? Yes. So there are 3 more examples on this slide, so you can read it at a later time. So you can fill this table at a later time, so I'm not going to spend time on this. So you have the answers on my presentation. So this is what I have explained earlier, the rule. So when you do the multiplication and division, it's going to figures significant figures. Yes, so that's another example. So it's a multiplication and division. So we are going to count the number of significant digits. So this has 3, this has 2, and this has 3. So previous number of significant digits in the calculation is 2. The calculated display is 3.4305. So all those decimal values, but the correct answer is 3.4. So this is going to be the correct answer into two significant. Any question? Okay, so sometimes you might need to add a zero to get the appropriate number of significant digits. So if you type 6.0 divided by 2.00 on your calculator, your answer is 3. But based on the significant rule, we have two significant figures for 6.0 and we have 3 for this. So first is 2. We have to write 3 into two significant digits, so it should be 3.0. That's the correct answer. So if I give you 3 and 3.0, correct answer is 3.0. So you have to follow the significant rule until your first exam. After that, you don't need to worry about significant rule because I'm not going to test you on significant figures and rules. So this is a simple practice problem. So it's a multiplication and division. Do the calculation using a calculator and write the answer into appropriate number of significant figures. What is the answer? Calculation. So when you multiply 5 times, calculated display is 8.52. The calculator. Now we are going to count the significant digits in these measured values. So how many is 5.00? Raise the significant figure. So how many in 3.408? 4 and 2.0? 2. So biggest number of significant figures in the calculation is 2. So now we are going to round this number into two significant digits. 8.5 centimeters. Definitely there will be one question like this in the exam. Okay. The next one is the addition subtraction rule. So during the addition and subtraction, also retain the first decimal place. So as an example, so we have 1,000 place in this number, 100 place, 10 place. So calculated display answer breaking into 10 place accuracy. The correct answer is 6.66.1. Now the example, it's true for subtraction. So when you subtract 65.09 minus 3, answer is 2.09. So now we are going to round this into tens place. This is the lowest number of decimal place. Answer is 62.1. So that's the practice problem in the next slide. Yes. Do the addition and write the answer if you have a great number of digits. What is the answer? Calculated value is going to be 904. This has one decimal place. We're going to round this number into tens place. 4.4. Any questions? Okay. So dimensional analysis or unit analysis, or some people call this as railroad method. So we use this technique to convert a given unit into a new unit. So we are going to start from a given unit. In this example, it's meters. So then we can convert into a different unit. So that's a required unit or needed unit. So when we convert a given unit into a different unit, we need some equations between given and needed unit. So those equations are called equalities. So there are a couple of places to find those equalities. So I will show you a table. So it's on your slide 76. So there are a lot of equations. And you're going to use some of those equations with the exam. And also some equations will be in the question. Okay. So we are going to use those equations to convert given unit into the required unit. So when we do that, we set up our factors. So we are going to set up conversion factors like this. So it's a ratio of two values, 2 units. So we set up those conversion factors based on the unit. So if you're not going to write your unit after the number, you are not going to understand this concept. Okay. So that's why unit is important. So always you have to write your unit with the value. So let me start from a simple example. Okay, so I'm sure most of you will be able to answer this question, but I'm going to explain it from beginning. Okay, so as an example, let's say we want to convert 12.5 kilograms into, okay, let me use it as 12 kilograms into pounds. Okay, so this is going to be my given unit. So let me write this in word. So how many pounds in 12 kilograms? So this is my question. Okay, so you're going to get a question like this. So then, once you read your question, you will be able to identify your given and needed unit. So in this question, given is kilograms. That's it, unit. And always we have a value to start with that given unit. So it's 12 kilograms. So required is how many pounds? So need is pounds. Okay, so now we are going to find an equation between given and need. So go to slide 76, there's a table, and find an equation between kilograms and LB. So what is that equation?
Equals 2.20.
1 kilogram is equal to 2.20 LB. Okay. So that's the correct equation. So in this equation, we have given unit on one side and unit required on the other side of the equation. Sometimes we might not find a single equation like this between given and need. So in that case, we are going to use more than one equation. So I'll do more examples. So this is a simple problem because we can do it with one equation. So let me show you why we are going to use these factors, and then I will explain how to set up the calculation. So this is our equality or equation. So I'm going to use 1 kilogram equal to 2.20 equation and divide both sides of this equation by 1 kilogram. So this is a simple equation. So we can divide by the same value and it's going to be a valid equation. So what is the answer on the left side when you divide 1 kilogram by 1 kilogram? 1. And this side, we can simplify it further. So it's going to be a ratio of 2 values with 2 units like this. So these type of ratios are called conversion factors. So we can use this conversion factor to convert kilograms into LB. And I will show you how to do that. So this is called the conversion factor and it's equal to 1. So this is going to be the next one. Okay, so I'm going to use the same equation. 1 kilogram is equal to 2.20 LB. And this time I'm going to divide by right side. 2.20 LB. So I'm going to divide both sides by 2.20 LB. So what is my answer? 1 kg over 2.20 LB. I can't simplify this side further. So I'm going to keep it like this. And the right side is 1. It is also equal to 1. So if you pay attention to these two ratios, it's simply right side of the equation divided by left side equal to one. The left side of the equation divided by right side of the equation equal to one. So this work is not necessary, but I want to show you why we are going to use these factors. So both of these factors are equal to one. So depending on the question, we are going to use one of these factors to convert kilograms into LP. And this is how we are going to set it out to do the calculation. So we always start from the given value and its unit. Okay, so 12 kilograms. And if you want to see this as a ratio of two values, you can simply put a line and write it like this. So dividing by one doesn't change anything. So if you want to see that as a ratio, so then you know the numerator and denominator. So numerator is the top value, denominator is the value in the bottom. So then I'm going to multiply this by one. Did I change anything? No. So instead of this one, I'm going to use one of those factors. So these are my factors. 1 kilogram is equal to 2.20. LB is equal to 1. And 2.20 LB equal to 1 kilogram is equal to 1. So these are the two factors that I showed in the other slide. For this one, I'm going to replace by one of these because it's equal to 1. So 12 kilogram for 1 times. So when I'm selecting my factor, this is the important part, your unit. So unit is kilograms. And I'm going to keep the kilogram in the denominator because when we have the same number in the numerator and denominator, it cancels out. Like 2 divided by 2 cancels out on this 1. So when we have the same two values in the numerator and denominator, it's always 1. So it is same for units. So when you have the same number in the numerator and denominator, it's 1. So now I need the value. So kilogram in the denominator value is 1. Now we know the value goes into the denominator, so it's 1. And the other side of the conversion factor is 2.0 LB. So then cancel the units, right? This kilograms to kilograms cancels out. So we don't have any more kilograms in the calculation. Now this is a simple multiplication and division. So 12 times 2.20. So everything in the numerator multiply together. Divide by 1 times 1. Everything in the denominator multiply together. So it's the multiplication between this. So 1 times 1 is 1. So then you divide the numerator by denominator. So 12 times 2.2 is 26. Exactly. 26.1.
4.
Okay. So then over 1. So dividing by 26.4 by 1 is 26.4. And unit is LB. So this is the remaining unit. The final unit is LB. This is not going to be the final answer. That's it. That's your calculator value. So this is a multiplication and division. So we are going to apply the significant rule. 12 kilograms measured value as of something. So how many significant figures? And if your equation is in the last column in that table, slide 76 table, it is from the last column, except the first one. One side always has some odd values like 2.20 or 0.621. So there are some odd values like this. So those are measured values because kilograms is in the metric SI system, unit system. And this is US unit system. So we are going to take 1 from this metric. So that's our reference point. And then we measure this 1 kilogram using the US scale. That's why we have 2.20. So it's a measured value. So we have to count significant figures on this side. That's 3 significant figures. So this is the definition 1 kilogram. Okay, so there's a reference of 1 kilogram in Europe. So I don't remember the exact place. So we can measure that using the US system. So this is the exact value, measured value. So answer written into the fewest number of significant figures. So 26.4 into 2 significant figures, answer is 26 LB. That is how we convert any given unit into a new unit. So sometimes it's just one factor, sometimes it's more than one factor, but technique is same, so always we cancel out the existing unit until we get the required unit. Okay, let me go to that slide with the type equations, explain this. Okay, so since this is between two different unit systems, this is a definition, okay, so that's why it says exact on both sides, right? So these are measured values. So you must consider significant digits on these values. So one is the reference value, the other side is the measured value. So one is always exact. But if you're going to pick your equation from one of these two columns, you're not going to count significant figures because these are definitions. So these are exact values. So don't count significant figures on this equation, but you need to count it on the last column. Does that make sense? Or do you want me to explain it again? Okay. So let's go back to my slide. So in this example, it shows us two conversions to convert meters into centimeters, because sometimes we have to use more than one factor to convert given unit into the needed unit. Because sometimes it's very difficult to find how many inches in a meter. Yes, it is sometimes difficult. So that's why we convert meters into centimeters. So this is a simple equation that we can derive from the value of prefix, and I'm going to show you. So then we can use the centimeters to inches. So it's in the last column in the next table. Okay, so let's do one from this conversion. So this is your second example. How many inches are in, let's say, 15 meters? So once you analyze your question, like 50% of your question is done. So first you need to identify the given value and unit. So there's only one value and one unit given with that value. It is 15 meters. So always make sure to write your unit. Then need. The need is how many inches. So this is the required unit, inches. So that's the unknown quantity. So then you can go to the table and find the equation between meters and inches. So, okay, so in that case, you have the equation. So 39.4 inches is equal to 1 meter. So we can use this equation to convert 39 meters into inches. If not, so someone else can find a different part. So you can use. Do you have centimeters? Yes. So someone might think like this. So we can convert 1 meter into centimeters. Okay, so this is the part. Meters into centimeters. Because we have this equation. So then there's another equation in this table. Centimeters into inches. Both method will give you the same answer. So one can do the calculation in one equation using this one. But if not, you can use both of these equations. So this converts meters into centimeters, and this converts centimeters into inches. So I'm going to use two equations and show you how we are going to set up the calculation. So the method that I'm going to use is meters into centimeters and centimeters into inches. So basically, when we don't have a single equation between given and needed unit, we find a common unit that can connect both given and needed. So centimeter connects to meters through this equation. So 1 meter is equal to 100 centimeters. So meter into centimeters, meter and centimeter, that equation. So this side is centimeters into inches. So we can use this equation. 1 inch is equal to 2.54 centimeters, and both of these values are that value. So then you don't need to write all the conversion factors. Each gives us 2, so which means we have 4 conversion factors. So I'm not going to write all 4. So then we can set up our calculation like this. So given value is 15 meters. And if you want to see it as a ratio, write it like this. multiplied by another ratio. And that ratio is going to be out of this equation. So this is the important part, given unit. I'm going to keep the same unit in the denominator. Because we have the same thing in the numerator and denominator, it cancels out. So then we need the value. So go to the equation, either value with one. So that's how you decide which value is going to be in the denominator and numerator. So once you decide your denominator based on your unit, the other side of the equation is in the numerator. So this goes here. So now we converted meters into centimeters. So if we simplify this, we get the answer in centimeters. But that's not our target. So our target is inches. So we are going to use another conversion factor. This time, existing unit is centimeters. So then we are going to use another factor, convert centimeters. Then we can calculate it like this. So our required unit is inches, so it should be on top. Then values, go to the equation, inch with 1, centimeter with 2.5. That's it. So we converted meters into inches. So now we are going to multiply everything in the numerator together. So it's going to be 15 times 100 times 1. So multiplying by 1 doesn't change anything. And again dividing by 1 doesn't change anything. 2.54 and unit is inches. So calculate value is 15 times 100 divided by 2.54. Answer is 590.55118. So 590.118. But this is not our final answer. So this is a multiplication and division with some measured values. So this is the length of something. Okay, even though it is not specified, it could be length of anything. So it's a measured value. It has two significant figures. Equation from metric or SI. Both are exact values. This is exact. Okay, so in the last column, this is the exception. Both of these values are exact values. So we do not count significant figures. Okay. So then there's only one measured value. It has two significant figures. So we are going to round this into two significant figures. What is the answer? 590 like this without the decimal point, so it has two significant figures. For answer in scientific notation. Both of these answers are correct. Anything else? Any question? Good. So it doesn't matter how many factors you are going to set it out. So it's always based on the remaining units. So you always set it to cancel out. So both unit that you're going to cancel out should be in the numerator and denominator. So otherwise you can't cancel it out. Okay, it's time to do more examples. So the process of problem solving in chemistry often requires one or more conversion factors to change a given unit to the needed unit. So problem solving requires identification of the given unit, given quantity and unit needed, conversion factors that connects the given and needed units. So let me give you a practice problem. Third example. How many ounces are in, let's say, 5.4 kilogram? How many? Getting answer is not the important, so the method is important, so answer is which one? Answer is not the important part, so the method, I want you to understand the method. Is there any single equation between ounces and kilograms? No, so then you need to find a common unit that connects ounces and kilograms. So what is that common unit? Pounds, yes, you can use pounds, so LB to connect. The given in kilograms value is 5.4. It is ounce, since we don't have a single equation, find a common unit that connects both. You have equations for both of these. So kilogram and LB, so 1 kilogram is equal to 0.20 LB. That's the equation. So this is LB to ounce. So how many ounces are in a LB? 1 pound is equal to how many ounces? 16 ounces. So next, we are going to set up our calculation. So starting point is always the given value 25.4, and its unit is kilogram. We can think it as a ratio multiplied by another ratio. That ratio is equal to 1, and it comes from this equation. So when you set up this conversion factor, this is the most important part. So if we don't have this unit, we don't know whether 2.20 is in the numerator or in the kilogram must be in the denominator. Value is kilogram is 1. The other side of the equation on top. Okay, so kilogram. That's allowed. Next factor converts LB is the existing unit, so it should convert it LB into ounces. So LB value is 1, so it's going to be the denominator. Ounces have 16, it's the numerator. So LB value. Then we're going to do the multiplication, so it's going to be 25.4 times 2.20 times 60. And denominator is 1 times 1 times 1, so it's just 1. And unit is ounces. The calculator value is 894.08, and unit is ounces. If it's not your final answer, go to the calculation and look for the measured values. So this is mass of object. So it has 3 significant figures. It's 1 exact, 2.20 measured, 3 significant figures. 1 and 16 both are exact values. So both has 3 significant figures. Answer it into 3 significant figures. It should be 894. Any question? Did everyone understand this method? Okay, so probably in this chapter, this conversion might be easy because units are somewhat familiar units. But in chapter 2, we are going to use some odd units like atoms, moles, molecules, grams. So that's why I want you to understand this method. So if you can't identify your units in your calculation, you will be in trouble in chapter 3. So I'll do a lot of examples like this. So please, you need to understand this method. Okay, so this is a simple example. So you have all the work on your slide. So I'll quickly go over this. So if a person weighs 164 lb, so these are the basic steps for the calculation. Step 1, Right? You're going to analyze the question and identify given and needed unit. And it is asking what is the body mass in kilograms? So kilogram is the required unit. So since these two units are in metric and US unit system, so you can find a single equation to convert US metric conversion. So that equation is the next one, step 3. So finding out this equation. The given unit is on one side and required unit is on the other side. And that equation gives us two conversion factors. And then we are going to set up the calculation based on the given unit. So given unit is LB. So we have LB in the denominator to cancel the given unit. So this is the mass, body mass of that person. So it has 3 significant figures. And 1 kilogram is the exact value. And 2.20 has 3 significant figures because it's from the last column. So answer written into 3 significant figures. Okay, this is another quick question. Convert 8.44 meter long, rattlesnake is 8.44 meter long, and how many centimeters long is the snake? What is the answer?
You could do 4.1 times.
How did you get that? But 2.44. Yes, that is correct. So given unit is meters, so you can write it like 1 over. So then we are going to use this equation. So equation is given in the equation. So this is the important part meter. The meter has 1. So 1 meter is in the denominator. The other side of the equation on top. So like that. So 2.44 times 100. Answer is 244. You can write it like this. So in scientific notation is 2.44 times 10 to the power 2 centimeters. Both the answers after it. Any question? So you can see all the work on my slides. Yes, so in that case, the measured value is 2.44 because it has 3 significant figures. So answer written into 3 significant figures. So 1 meter and 100 centimeter, both the exact values because those are definitions. Okay, so this is the dimensional analysis in brief. Always, that's a always we cancel out the given unit, kilometer to kilometer, meter to meter, centimeter to centimeter, then we get millimeters. So if you want to convert kilometers into millimeters, so we can use 3 conversion factors like this. So 1 kilometer is equal to 1000 meters, 1 meter is equal to 100 centimeters, 1 centimeter is equal to 10 centimeters. Okay. Any question? So in problem solving, 2 or more conversion factors are often needed to complete the change of unit. Set up these problems, one factor follows the other, and each factor is arranged to cancel the preceding unit until the needed unit is obtained. So in this class, the longest that we are going to set up is up to 4 conversion factors. So if you prefer to do it in step by step, you can do it. But when you do the calculation in step by step, sometimes you might add some rounding errors. So in this calculation, you are not adding any rounding errors, but we're going to do this calculation in one step and find the answer and then use that value in the next conversion. You're going to add some rounding errors. So at the end, you might have a deviation from the final answer based on how you're going to round your numbers. So I always prefer to set up all the calculation in one step like this. So then do the calculation in one step. So in that case, you get the correct answer without any rounding error. Okay, so one way to find those equations is from this table. So this table will be on front page. Okay, you don't need to memorize any of these equations. because I'm going to give you the exact same table on your front page during your exam. So if you can't find a conversion between two units from this table, then it will be given in the question as a statement. So you should be able to identify those statements. So there are some equations in this question. So actually there is one. So we are going to identify that equation. So when you read this question, it says a doctor's order prescribed a dosage of 0.150 milligrams. So that's the prescribed dosage, and that's going to be your starting point. So that's the required dosage for the patient. But in the next sentence, it says if tablets in stock contain 75 micrograms of synthroid. That's a statement, and it's an equally. If tablets in stock, so if we take one tablet, it has 75 micrograms. So you can write micrograms like this or like this. Yeah, I always write micrograms if we break like a micro. Okay, so you should be able to identify these type of statements as equations. So it's applied to this particular problem. So it's valid for another question. So in this case, it is asking how many milligrams, I guess. I don't. How many tablets? Oh, sorry, it's asking how many tablets. So that's it, required unit, the number of tablets. So given milligram. So we don't have any direct equation between milligrams and tablets, but once you identify this statement as an equation, you can say it converts tablets into micrograms. So that's your connecting unit. So you have micrograms you connect for tablets and milligrams. So milligrams to micrograms, it's in the table on slide 76. So this conversion is in the question. Micrograms to number of tablets. So this is the equation. One tablet is equal to 75 micrograms. Okay, so let's quickly go over this question and understand how do we set up the calculation. So let me summarize that question. Given 0.150 milligrams, the number of tablets. Okay, so that's a statement in the question, and it says one tablet in stock contains 75 micrograms. And also this is another hint for your connecting unit, because micrograms connects to tablet, and also we can connect milligrams into micrograms. So this is given in the question, and this side is required from the table. So what is the equation between milligrams and micrograms? 1 milligram is equal to how many micrograms? Also milligrams. Oh, micrograms, sorry. Micrograms. Okay, so now we can set up the calculation because we have all the equations and the path to convert given number into the given unit into the needed unit. So once you can understand this part of the question, so you're like 50 to 75% of your question is done. Because next step you are going to set up the calculation and find the answer. So this is how we are going to set it out. 1.50 unit milligrams, and take it as a ratio. Now we convert milligrams to micrograms because this is the common unit between tablet and milligrams. Now we need the values because we can cancel milligrams to milligrams. So 1 milligram, 1000 micrograms. But we're going to set it like this. Next one converts micrograms into tablets. So we should have micrograms in the denominator and tablets on top. So microgram 75. That's the value. Tablet 1. Okay. So final answer is going to be in tablets. And you can do the calculation. Answer is 2. And in this question, you don't need to consider significant figures because tablets are counting numbers. Those are exact values. So it's going to be 2 tablets. You don't need to worry about significant figures in this question. Tablets are exact values. Okay, so you have this question on your slide. All those work. These are the equations, and this is how we are going to set it out. And these two tablets. Any question? Okay, so this is another problem like that. So you don't find the equation in the table, but I think you can find a way to convert number of days into minutes. And also consider significant figures in your final answer. I'm sure everyone can get the answer, but think about the significant figures in your final answer. Answer is not 2016. Calculated value is 2016. After your first exam, you can drop all the significant figure problems. I'm not gonna talk about significant figure after first exam. One more week left. But it's 1.4. They need these minutes. So how do you convert days into minutes? Yes, so we can convert days into hours and hours into minutes. So 1 day is equal to how many hours? 24 hours is equal to 1 day. The next one, 1 hour is equal to how many minutes? 1 hour is equal to 60 minutes. So now you decide how you are going to convert days into minutes. So first we are going to convert days into hours, hours into minutes. The next step we are going to set up a calculation starting from the given value, so 1.4 day. It's time for something. Or as a ratio, multiplied by a factor from this. So this is the important part. Day must be in the denominator. So that is this one, then hours. Day and day cancels out. The next one convert hours into minutes. Hours into minutes. 1 hour 60 minutes. So this is going to be 2060 minutes. So we are not done yet because we need to consider significant figures. 1 hour is exactly 60 minutes. These are exact values, exact. 1 day exactly 24 hours, exact. This is going to be the measured value, so it's bottom. Time for something. So it has two significant figures. And how do you round that number to two significant figures? Scientific notation. So that's the only way you can write this into two significant figures. 2 and 0, so those are the required digits. So we are going to drop 2 digits before the decimal point. So we are going to add 2 zeros, but if you write 2000 like this, it has only one significant digit. So you have to convert this into scientific notation. 2.0 times 10 to the power 3 minutes is the answer. Any questions? All my examples may have some tricky point like this because I want to cover all the topics that we learned. So in the exam, I'm not going to make it like so difficult. But I would like to point out everything that we learned from the lecture. Yes, the answer is 2.0 times 10 to the power 3. So another problem. The if your pace on a treadmill is 65 meters per minute, how many minutes will it take for you to go a distance of 7.5 kilometers? There's a statement in this question and it's going to be an equation. So what is that statement? So what is the equation? So it says 65 meters per minute. Okay, so 65 meters per minute means it's going to be a ratio. So ratio of 2 units always a factor. So this converts minute into meters or meters into minutes. So this tells us 1 minute of pace is equal to 65 meters. So you should be able to identify equations like that. Okay. So this is going to be a starting point. So that's a given value and its unit. So given is going to be 7.5 kilometers and need is time in minutes. So how many minutes it will take? So that's a required unit. So once you identify this as equation, so you have your connecting unit, so that's meters. So we convert kilometers into meters, minutes into, meters into minutes. So this is in the table, 2 different units with the prefix. So 1 kilometer is equal to how many meters? 1000 meters. Even you can get it from the prefix value. So kilo is 1000. You can get it from the prefix value. So this is the equation given in the question for this particular problem. The 1 minute is equal to 65 meters. Now we can set up our calculation like this. Kilometers multiplied by a factor, kilometer, kilometer. And meter should be the numerator. Kilometer value is 1, meter value is 1000. 1000 is 1000. Kilometer, kilometer. Next factor converts meters to minutes. Meter should be in the denominator because of this. The existing unit is meter, so we must have the same unit in the denominator. Value of meter is 65, time is 1000. Now we converted kilometers into time in minutes. So it's 75 times 1000 divided by 65. I think calculator value is 115 point. What is the calculator value? .5 times 1000 divided by 65. 115.3846. It's not the final answer. The measured value, that's the working distance, two significant figures. 1000, both are exact values. So this is the pace, so it's a measured value, so it has two significant figures. Exactly. So, two significant figures. What is the answer? 120. So first two are the required significant digits. First number to drop is 5. So add 1 to the first written number. So it's become 1, 2. And we are dropping a number before the decimal. So replace it by 0. So 120 has two significant digits. Question. The answer is 120. That's end of the chapter 1 lecture slides. Any question?